So we're now going to try a Lagrange multiplier problem where we've got three variables, x, y, and z, coming up in the problem. So in other words, it's a three-dimensional problem as opposed to a 2D problem. We're going to find the maximum volume of a rectangular box that can be inscribed inside a certain ellipsoid. So let's start by drawing a picture of this ellipsoid. So 3D space, if we wanted to think about some intercepts here, could set y and z equal to 0, figure out what that would mean for x. So x squared over 4 would have to be 1, meaning x could be plus or minus 2. So I'm just going to draw the positive x-intercept. Okay, so that would be 2. In a similar way, you'd have a positive y-intercept of 3 and a positive z-intercept of 4. All right, so if we wanted to get a visual on this ellipsoid, you could, in the xy plane, draw an ellipse. Looks like it would pass through those two intercepts. You could say in the YZ plane, draw another ellipse. That looks like it would pass through those two intercepts. And then you can just complete your picture by going around the outer edge of this drawing here. Okay, so roughly something like that. There's kind of a visual on our ellipsoid. So the idea is that we want to put a rectangular box inside this ellipsoid just so that the corners of the box are sitting right on the edge of the ellipsoid surface. So in order to not overcomplicate the drawing, I think I'm going to redo the ellipsoid. Let's just say we're looking at it from this perspective. Okay, and then we want to have a rectangular box sitting inside this ellipsoid. So let's say, a rectangular box might look something like this. This is just a very rough drawing, but what I want to emphasize is that the corners would be sitting on the surface of that ellipsoid. If they weren't, then that would suggest that you could make the box slightly bigger to fit a bigger rectangular box inside there, and definitely the corners should not be extending beyond the surface of the ellipsoid. So the question is, what is the biggest volume of this box? As we change the dimensions, that's going to affect the volume. So what combination of dimensions for this box are going to allow it to have the corners sitting right on the surface, but maximizing the volume of that box? So just like in our previous problem, we need to introduce some variables here in order to do a calculation. So let's look at the vertex that would be sitting closest to us. So that would be one of the front vertices, it would be the top vertex, and it would be the vertex over to the right. Or you could actually say this is the vertex that's sitting in the first octant, where x, y, and z are all positive. So let's call that x, y, z. So the idea is that if we look just in the y direction, if we're saying one of the corners of the box is at this y coordinate y, then the other coordinate is going to be at minus y. Or if we just say this a little more intuitively, if you measure the length of the box in the y direction, it's actually 2y. And same thing, the depth of the box is going to be 2x and the height of the box is going to be 2z. So if we write down our volume of this box, it's actually 2x times 2y times 2z, or in other words, 8xyz. And what we want to do in this problem is we want to maximize this volume. Okay, the constraint that we have is that the corners need to lie on that ellipsoid. So the constraint is just the equation of the ellipsoid. So the x squared over 4 plus y squared over 9 plus z squared over 16 equals 1. So I'll highlight both of those because we know that our function that we're trying to maximize and our constraint are the two important aspects that we're going to need for the calculation. So if you like, you can call the function that you're trying to maximize f, just because that's the notation that we used when we introduced Lagrange multipliers. And when you're talking about your constraint, it is important to have it in the form g equal a constant. So we've got a 1 on the right side. If for some reason you had variables on the right side, then just move them over to the left before naming your g. So G is all this stuff on the left side there. Okay, and then we're good to go with our Lagrange multiplier procedure. Let's try it. So we want to take the gradient of f and say that's equal to lambda times the gradient of g. So gradient of f, 8yz, 8xz, and 8xy. So those are our partial derivatives of f with respect to x, y, and z. Okay, and then we're going to say that's equal to lambda times, we're going to take the gradient of g. So just looking at the left side of this ellipsoid formula, let's take our partial derivatives. So 2x over 4, 2y over 9, and 2z over 16. Okay, I'm not going to worry about simplifying yet because I know there are going to be a lot of equations coming down the pipeline. So from this setup, we are going to get 3 equations, one from each of these vector components. So let's see if we can deal with those equations one by one. So first equation is going to say something like 8yz equals lambda times 2x over 4. So that's just saying the first component of the vectors from each of the sides of this equation must be equal. Okay, and we saw in our previous problem that we're going to be solving for lambda, and down the line we're going to be setting all the lambdas equal to one another. So by solving for lambda in each equation, that's what allows you to let the different equations interact with one another. Okay, so let's just do a little bit of algebra here. Lambda would be 8yz times the reciprocal of 4 over 2x. So let's call that 16yz over x. So that's one of our lambda values. And we're going to do the same thing for the other 2 equations and get our lambdas. Okay, so let's try the second one. 8xz is going to be lambda times 2y over 9, solving for lambda. 8xz times 9 over 2y, so 36xz over y. And then finally 8xy equals lambda times 2z over 16. That implies that lambda is going to be 8xy times 16 over 2z, which is equal to 64xy over z. Now somewhere on the side here, we should write down our 4th equation, which is the constraint, just the equation of that ellipsoid that we were working with in the problem. So that was x squared over 4 plus y squared over 9 plus z squared over 16 equals 1. So I consider this a separate type of equation because it doesn't have a lambda in it, whereas the first 3 equations all had lambdas in them. Okay, so this is in general how we're going to deal with one of these problems where we've got 4 variables. We've got our x, y, and z, plus we've got our lambda. So first thing we're going to do is from the 3 equations, we are going to say lambda equals lambda equals lambda. And that's just going to get rid of the lambdas for us. So from the first equation, 16yz over x, that is the same thing as from the second equation, 36xz over y, and that is the same thing as 64xy over z. So now we can scroll up. We don't need to look at those first 3 equations anymore. And the idea is to get 2 of your variables in terms of a single variable. So if you want to say this concretely, you could say get y and z in terms of x, for example. So our goal is to use this sequence of equations that we've got here to just get rid of y and z, turn it into, turn them both into expressions involving x, and see once we have y and z both in terms of x, then we could take that and plug that into our constraint. That would give us x, and then we would very quickly get y and z from there. So this is probably one of the trickiest parts of the problem, is just when we go through this process of getting y and z in terms of x. So here's what we'll do first. Let's break it into two stages. So let's look at these two things. Okay, 16yz over x is equal to 36xz over y. So we're just going to do some calculation here and see if we can simplify this. So I would be tempted to cancel out the z here. We know that z is not equal to 0. Because if z were equal to 0, that would mean our rectangular box has no height, and that would produce a volume of 0. That's clearly not going to be the maximum volume. So we can rule out the possibility that z equals 0 and just divide through by z. So that says 16y over x is equal to 36x over y. Okay, now we can cross multiply. 16y squared equals 36x squared, or y squared equals 36x squared over 16. All right, well, our goal, what we're looking towards, is eventually being able to go back to the constraint and just get everything in terms of x. So I would say it's not necessary to fully solve for y here. It's good enough just to get a y squared, because we'll be able to take that, put that back into our constraint, and we'll have something entirely involving x. So we've done enough work there. I'm going to put all this stuff in a box. And I'm going to highlight this fact that y squared equals 36x squared over 16. We've taken that far enough. So now we want to do a similar kind of thing where we get z in terms of x. So I would say kind of a slick way to figure out how to do this, we need an equation that we can cancel y out of, because we really want to come down to an equation involving z and x. So if you look back at this sequence of equations that we got up at the top of the screen here, see, if you said that the first and the third things are equal, let's do that over on the side. If you said 16yz over x is equal to 64xy over z, notice that y is going to cancel out of this equation. So certainly these things are equal because the sequence of three things that we've got up at the top of the screen, all these are just different ways of saying lambda. So these two quantities are certainly equal, but I chose the two quantities that both had y in them so that we could just cancel out the y. So by same argument as before, y is not going to equal 0. Otherwise the box would not extend at all in the left-right direction. The volume would be 0, and that's not going to be our maximum volume. So we can say 16z over x equals 64x over z, cross multiply, 16z squared equals 64x squared, and sure enough, we're getting a little formula for z squared. So z squared is 64x squared over 16. So we have managed to write z in terms of x. And similar to our discussion before, we don't need to go all the way to solving for z, because if you look back at our constraint, which we've got now right up at the top of the screen, the constraint actually involves z squared as opposed to z. So it's going to be good enough just to solve for z squared there. Okay, so let's put this stuff in a box. And see, now we're all done with the lambdas, because the lambdas were just a tool to help us figure out how is y related to x and how is z related to x. So now that we've got everything in the language of x, we're just going to go to our constraint, we'll get x, and we'll very shortly after that have our solution. Okay, so here's our fourth equation, the constraint that we haven't used yet. X squared over 4 plus y squared over 9 plus z squared over 16 equals 1. Let's shove everything in here and we'll see what happens. So we've got x squared over 4 plus, we've got 1/9 of whatever y squared is. Well, from the highlighted thing on the left here, we've got y squared is equal to 36x squared over 16. Great. And then we've got 1/16 of z squared. Well, from the right highlighted section here, z squared is 64x squared over 16. Great. So all this stuff here is equal to 1. So let's see if we can clean this up. We'll just do a little bit of simplifying of the coefficients here. So in the second term, you could call that entire thing x squared over 4 after you do your simplification. So 36 over 9 was 4, and then 4 over 16 gave us the 1/4. Okay, and then same deal here, 64 over 16, 4, and then 4 over 16 leaves us with 1/4. Okay, so from there, we should be able to finish off the problem. So that's 3 x squared over 4 equal to 1. Let's multiply both sides by 4/3. So x squared is equal to 4/3, and that means x is equal to plus or minus the square root of 4/3. Okay, now in this problem, we're talking about lengths. So we can insist that x is going to be positive. So we can take the positive root here. So x is going to be root 4 over 3. If you distribute the root to the top and the bottom, you'd say root 4 over root 3. So 2 over root 3. And you could rationalize that, and you could say 2 root 3 over 3. Okay, so that's a little bit of fun with radicals there. So that's our x value. Now from there, we should be able to get our y value and our z value quickly. So let's highlight that. We're definitely going to want that at the end of the problem. So now that we've got that, let's see if we can get our y and our z. So let's go back to the equations that we had a little bit earlier. Remember where we solved for y and z in terms of x, and we highlighted those. So that was smart to highlight them because we're now going to use them. So y squared equals 36x squared over 16. Okay, let's just go back to where we said x squared was equal to 4/3. So we got 36 over 16 times 4/3. We'll just simplify that and figure out what y squared is coming out to. So if you try this on your calculator, that comes out to 3. That tells us y is going to be either plus or minus root 3. But again, because it's representing a length or a dimension of this box, then we can say y equal root 3. Okay, so y equal root 3. We know x is equal to 2 root 3 over 3, so we're almost there. Now we just need to get z. So again, let's look back to that equation where we had z in terms of x. We had that here. It is a good idea to kind of highlight it or put a star on it whenever you get it, because you will look back on it later. So z squared is 64x squared over 16. Okay, that's z squared. So z squared, 64x squared over 16. 64 over 16 is actually 4. We just didn't simplify that before. So we are getting 4 times our x squared value, x squared being 4 over 3. Okay, so that tells us that z squared is 16 over 3. We can say z is equal to either plus or minus square root of this quantity. So just taking square roots of the top and the bottom, that would be 4 over root 3. We can choose the positive because we know that as a dimension of this box, z is going to be a positive quantity, and then we could rationalize that and say 4 root 3 over 3. Okay, so there's our z value. All right, so now we're ready to write down our answer. So the question was, find the maximum volume of the box. And our function giving us our maximum volume, remember, was 8xyz. So we're just going to multiply 8 times each of our dimensions here, and we'll have our answer for the maximum volume. Okay, so just scrolling back for a second, we said x was 2 root 3 over 3. We said y was root 3, and we said z was 4 root 3 over 3. So if we multiply all this out, the integers, 8 times 2 times 4 gives us 64. We've got a root 3 on there. 2 of the root 3s on the top, let's say these two, are going to cancel with a 3 on the bottom. So 64 root 3 over 3 is our answer. We don't have units here, so we'll just leave our volume like that. And when you are answering these kind of questions, it's nice to give the maximum or minimum value of the function as well as the point where it's achieved. So you could say achieved when, and then just give your x, y, z values as an ordered triple, so it's easy to pick those out. So 2 root 3 over 3, root 3, and 4 root 3 over 3 would be, geometrically speaking, this would be the corner of the box in the first octant.